All right. Real quick, here's the quiz. This was the solution to the quiz, 187, blah, blah, blah. How do we actually solve that? Blah, blah, blah. And here's the code that does it. And we're back. All right, so now some other bases.
Mid-class commercials
suck. Brought to you by Nabisco. Go with the host with the most. Go with the... I love that one. Everybody here has heard the first baseball game, right? Harry Caray calls the first baseball game. Who has not heard that? Have you heard Harry Caray calls the first base? Why didn't you raise your hand?
I didn't want to
Oh my gosh.
At least I twitched my fingers.
Man, do we have to listen to that? Try to think, is there any profanity in it? I don't think so.
Watched it in twice, right?
Yeah, I don't think there is. All right, real quick. I think this counts as Christian worldview, too. It's Bible stuff.
Yes, I recall.
Harry Caray, first baseball game. All right, here's the entire skit. This is 2 parts. If you haven't heard, some of you may have only heard part 1.
Hello, fans. This is Harry Caray. Welcome to today's game between the Bethlehem Braves and the Jerusalem Giants. Kind of a sparse crowd here today, as a plague of locusts has made it tough to get out to the ballpark. You can hear the vendors go, "Hey, manna, get your manna. Who wants bread from heaven? It's hot. It's fresh. It just fell. Hot manna here. Penance, penance, our fathers, Hail Marys. Can't get absolution without an act of contrition. Who wants a rosary here? Water. Water. What? Uh-oh. Wine! Who wants wine now? Peter looks into Jesus for the sign. Jesus gives him the sign. Holy cow! Peter denies it. He gives it to him again. He denies it again. Once more. That's 3 times, and Jesus is out to give Peter a sermon on the Mount. Jesus, of course, the big hero in yesterday's game, came up in the bottom of the 9th with the Braves down 3-0 and hit a bases-empty grand slam. Fans, we haven't had a miracle like that since we had fishes and loaves night. I had a chance to talk with the Savior after the game, and this is what he had to say. Well, Harry, the ball was on the outside part of the plate. I was not time to make contact. First of all, I want to thank my father for loading the bases. Muchas gracias, señor. And also the Holy Ghost for bringing up the double play. Back to live action. Lazarus up to the plate now. What's that? Oh, I'm sorry. Lazarus up to the plate now. Here's the pitch. Oh, no, he's hit. He's hurt. He's down. Holy cow, he's dead. But wait a minute. He gets back up. That's the 6th time this week. That kid can take one for the team. Abraham up to the plate now, probably up here to sacrifice. Infield drawn in for the Patriarch, and now there's some action in the Bethlehem bullpen. I can't quite make out the back of his robe. It is the big number 10, Moses, just called up from the Burning Bush League. Already gaining a reputation for that lightning-fast pickoff move, reminding those runners that thou shalt not steal. Let's give it over to Steve Stone. Thank you, Harry. Fans, you want to be here this Tuesday night when the Braves meet the Cavalry Cubs? It's going to be Nabisco Communion Wafer Day here at the ballpark. All fans 33 and under get a free Eucharist signed by the Sabres. You know, fans, Nabisco Communion Wafers go down smooth. Won't stick to the roof of your mouth like those cheap imitation sacraments. Sure, they cost a little more, but when it comes to your eternal salvation, isn't it worth that extra buck in the collection plate? Remember, fans, the next time you go to the rail for that body and blood, ask for the host with the most. Ask for Nabisco. Thanks, Steve. Here's some scores now from around the league. A big upset. David 1, Goliath nothing. Ends a long win streak for the big guy. Oh no, Job is on the 15-day disabled list with a bad case of leprosy. Pulled a hamstring. Pulled it right off. The Angels have sent Lucifer down. That's a shame. When that fellow was in his prime, he could throw some heat. This year, his earned run average has ballooned to a hefty 6. And here's the partial score. Sodom and Gomorrah still tied at 69.
Here comes the second part. Some of you may not have heard the second part.
Holy cow, what a rain delay. 40 days and 40 nights. I'm telling you, there's an ark in the parking lot that smells to high heaven. There's enough crap in that thing to fertilize the Gobi Desert. Out to cast the first pitch now, a fan favorite, he who has not sinned. A big hello to a special group out here at the ballpark today. 2,000 strong in the right field pavilion. It's the Meek. I love those guys. Blessed are the meek. In fact, when present ownership steps down next year, the meek shall inherit the team. Just a reminder, fans, this Friday will be a special giveaway for the kids. It's going to be John the Baptist bobblehead doll night here. Some assembly required. Calling balls and strikes behind the plate today, Solomon. And here we are, ready to go. Jesus looks in for the sign, and holy cow, wait a minute. Oh no, look who's running out to the field. It's Judas, the kissing bandit. He lays a big wet one on the Lord, and out comes Herod from the dugout, and he's out of here. The Savior's been removed from the game. I'm sure the scribes will have something to say about that in tomorrow's Bethlehem Star. Now, during this pitching change, I want to remind you the Sodomites are in town for a 3-game set this weekend. Good seats still available. This is one dangerous
Maybe I
ball
should
club.
pause it right. The end of that joke is a little questionable. So now everybody can say they've heard that. Some assembly required. John the Baptist bobblehead. Everybody gets that, right? Kind of chop the dude's head off. So the bobblehead, assembly required. Get it? Haha. So what got me thinking about that was the whole brought to you by Nabisco thing. The segues I take. All right. So when we think about data representation, in various bases, the ones we are most often here, let's see, common bases. Well, base 2, computers like this one. Decimal, which is base 10. Humans. And then base 16, hexadecimal. Who likes hexadecimal? Ram likes hexa. Okay, why would you say that?
Because that's when you're looking at it. When it tells you what location it is in the RAM, it tells you the hexadecimal number.
Okay, why?
Good question.
Is it RAM a computer part? Not a trick question.
Yeah.
Yeah, yeah.
Maybe so then have to give you this huge long. It's a shortened version, so then you have to give you this huge long address.
Okay, so hexadecimal might be kind of a hybrid, right? Where computers definitely like binary. Definitely like binary. But sometimes they need to display stuff to the user in a way that is readable by the user, but it's not something that is, I guess, mathable. You know, humans aren't going to do math with it. They're not going to add, subtract stuff to it necessarily. So they might show stuff in terms of hexadecimal, base 16. What's the advantage of hexadecimal? What's the advantage of base 16 over base 2? It's compressed. So even a medium-sized number in binary, we just saw it a few minutes ago. From the quiz today, this number is far less convenient for human beings than just saying 187. Correct? Far less convenient. Okay, so that's going from base 2 to base 10. If we go to base 16, it would compress even more. All right? So hexadecimal kind of sits in the middle. We could technically throw another one in here. Woo, hello. Say base 8, which is octal. Just say nobody. And that's not an entire truth, but you're not going to find this very often. Just happens to have a name associated with it, octal. Okay, so really what we're going to be concerned about in the computer hardware organization world is binary decimal and hexadecimal. The good news for us is we are already good at decimal. Remember, like back in before first grade when you had like introduction to numbers, right? You learned about decimal then. And all through our childhood until today, we've been learning about decimal. But now we're going to start counting in something other than decimal. Because decimal's boring. We're too good at it. So we need to move to things that we suck at and then get good at those. So we want to talk about converting between different bases, not just base 2 to decimal or decimal to base 2. So let's say that I want to convert from, and I'm going to still use octal as part of the example, and you'll see why here in a second. So let's say I want to convert the octal number to decimal. Now, octal, we go back here. We'll start with binary. Binary supports the digits 0 and 1. Octal supports the digits 0, 1, 2, 3, 4, 5, 6, and 7. So 0 to the base minus 1. Just like decimal supports 0 to 9. 10 minus 1 is 9. Those are the allowable digits. And we'll get to hexadecimal here in a few minutes. So if I want to convert 74 octal to decimal, how am I going to do that? Well, it's going to be a completely new algorithm that we've never seen before. Ever. So I'm going to steal some crap from this screen because you've never seen it, right? I won't need that many boxes, but I'm just going to take them. Seven, 4, kill everything else off. This is not 2 to the 0, this is 8 to the 0. This is not 2 to the 1, this is 8 to the 1 for base 8. So this is the 1's place, this is the 8's place. So this is 1 times 4 plus 8 times 7, which equals what? What's 8 times 7? 56 plus 4? 60. So 74 in octal is equal to the decimal number 60. Done. Wasn't this identical to what we did for binary? Same exact thing. Okay, let's go back into our code. Last time we wrote binary to decimal. Remember binary to decimal, we asked them to enter in a binary number. We typed it in. We read that number in as a string. We started off in the ones place and we multiplied by 2 each time. So we went from the ones place to the twos place to the fours place to the 8s to the 16 to the 32, the 64s, the 128s, 256, the 512, 1024, 2048, 4096, right? I just want to see how far I can go now. I'm tired. So we kept multiplying the place and we only checked to see if we were looking at a 1. Why is that? We go back to our example back here from our quiz. 10111 Notice down here, I only added numbers where I had a 1 in the place. Right? I skipped all the zeros. Why did I skip the zeros? 0 times anything is 0, and if I add 0 to anything, it's not going to change it, right? So why waste my time? But that was for binary. Binary only supports the 2 digits 0 and 1, those 2 bits. Oh, I'm jumping ahead. I don't want you to see that yet. Nobody saw that, right? Good. So binary supports 0 and 1. Well, now Octal supports 0, 1, 2, 3, 4, 5, 6, 7. A bunch more numbers, right? Well, that becomes problematic. Can I still ignore the zeros? Oh, sure, I can ignore the zeros. But all these other ones I actually have to do math with. With binary, I could just assume it was the base. You know, the current place we were at. If we were in the ones place, 1 times 1 is 1. If we were in the twos place, 2 times 1 is 2. Fours place, 4 times 1 is 4. So it was just the place. But what if I'm looking at the digit 2? The ones place would be 1 times 2 is 2 that I'd be adding on. So now I actually have to look at these values. Where the code we wrote previously, if it was a 1, I added the place to my sum. Otherwise, I ignored it. That make sense? The actual assumed thing here is I could have said place times 1 in there. And we just know that this is a waste of time because anything times 1 will be that anything. But that's what was actually there. But if I'm dealing with converting something else, so our example here, static int octal to decimal, and we'll steal first, actually steal all of it right now. We'll doctor it up. Enter. An octal number. We'll read that number in. We'll start our place off at 1, just like before. With octal, it goes 1's place, 8's place, 64's place. Start our sum off at 0. But now, we are not just interested in a 1. We're now interested in anything that's not 0, because I actually have to do the multiplication. That make sense? Okay, several different ways of handling this. The way I like to show with strings, I used to like to create a nice little map string. So this has all of the digits that belong to the octal set. So 0, 1, 2, 3, 4, 5, 6, and 7. Now, as a string, this 0 is at bucket 0. This 1 is at bucket 1. The 2 is at bucket 2. The 3 is at bucket 3. 4 is at bucket 4. So on and so forth. Okay? So this is more of a shortcut. If we were going to do this the hard-coded version, inside here I'd say if the character I'm looking at is a 1, add it to place. Else, if it's a 2, add in place times 2. Else, if it's a 3, add in place times 3. If it's a 4, place times 4. If it's a 5, place times 5. If it's a 6, place times 6. And finally, if it's a 7, place times 7. And we can assume that they'll enter in a legitimate, a legal octal number. So I've handled every single possible case here except for 0. Because we know 0 times anything will be 0, and therefore we're wasting our time adding it to our sum. That make sense? So here, I'll just comment out our map here for a second since I'm not going to use it yet. So I've doctored this code to now work on octal numbers. Last thing I need to do is, instead of multiplying my place by 2, I'm multiplying my place by 8. And in the end, I'll return the sum. So exact same pattern, but now we can convert from octal to decimal. Go ahead and test that. And what was my octal number from the example? 74. So, well, it's going to ask me. It's going to prompt me. So I'll run it, enter an octal number. I'm going to enter in a 74, and I expect it to give me a 60. There's the conversion. Make sense? Exact same algorithm, the exact same pattern. The only thing that changed is what my places were. Instead of it being the 1, 2, 4, 8, 16s, it's the 1, 8, 64, what is it, 256? 64 times 8, I think 256. 512. I've lost it. All right, so now to clean this up a little bit, to give us a further pattern, we can introduce another tool. Most of us have seen this, but some of us haven't, from strings called index of. So if I say, where is the index of 0 in that string? The index of 0 is at bucket 0. The index at 1 is at bucket 1. The index of 2 is at bucket 2. So that allows me to convert the character at a particular place in a string into its numeric equivalent. So I can get rid of all this crap. And replace it with sum is equal to sum plus place times map dot, I gotta uncomment map real quick. Map dot index of the num dot charat I. So as an example, when I read through my number 74, I'm walking it from the end, the 4, towards the beginning, the 7. That's this loop. Starts at the end of that string, keeps going all the way to the beginning of it, subtracting 1 each time. When I'm looking at the 4, this is the character 4. So it actually will be read in as the char 4, like that. Well, that's not equal to the number 4. I need to get the number 4 out of that. A couple different ways I can do it. I'll show one here real quick, and then we'll do another one. Again, data representation. So if I'm currently looking at a 4, that means the num.charat I is 4. So that guy there ultimately boils down to that in my little example here. So if I say map.index of 4, what that's going to do is it's going to go to this variable right here, map. It's going to find where in this string it sees the character 4, which is right there. And the character 4 happens to be at bucket 0, 1, 2, 3, 4. So this is that bucket 4 within this string. So that's a kind of a quick way of converting. Because of the order I put these characters in the string, I can say find 4, where is it located in that string? It's at position 4 in that string. So it'll let me do the math. All right, and then I'll multiply that by place. So that little trick there now allows me to do the exact same thing, but in far less code. Now, if you don't want to have to remember that type of thing, another thing we can do is instead of using map, we can take we can take the current character, which is the num.char@I. That's the current character we're looking at. And I can turn that into a string, taking the empty string, concatenating it to it. And then I could say integer.parseInt of that string. So I'll turn the character 4 into the string 4 and then tell the integer class to give me the numeric version of that. And we did that in one of the other things, didn't we? Did we do an integer.parseInt somewhere in here? Yeah, right here. With our get hertz. Okay, and again, this should give us the exact same output, just the means to an end was a little bit different. There's our 74, and there's our 60. Okay, what about converting octal? Converting decimal to octal. That is, getting the 74 back from our 60. Decimal to octal. We're going to take the 60. We're going to divide it by 8. 60 divided by 8 is 7.5. So that's 7 with remainder. 7 times 8 is what? 56. So 56 to 60 gets us a remainder of 4. Correct? 7 divided by 8. How many times does 8 go into 7? 0 times. 0 times 8 is 0 with remainder 7. Read your answer from bottom up. 74. Notice we're done when we hit a 0. Exact same pattern. Same thing as when we went decimal to binary. So I'm going to steal that code. And we're going to write decimal to octal. And instead of modding by 2, we're going to mod by 8. Done. Exact same pattern. Decimal to octal, and we want to pass a 60 for our example here. So we'll pass in the 60, and we should get 74 out of that. Just changing 2 little numbers in the same code. So again, we see a pattern. All right. So we just use the jump to octal as more of an instructional thing because, like I said, we will hardly ever use octal, but we do use hexadecimal, base 16. And guess what? Converting a hexadecimal number to binary, or to decimal, I'm sorry. Steal this again. start with my favorite hexadecimal number, BAD. So there's the B, there's the A, there's the D. We'll doctor the rest of this here in a second. Got to go back here to base 16. Well, we know that base 10, there's our human number, that's 0 through 9. It's the legal digits. But what about base 16? Base 16 will be 0 to 9. It will also be A through F. Okay? In number representation systems, we need to have each digit represented as a single character, whether that's a numeric character 0 through 9 or a letter A through Z. So we can deal with bases up to base 36. Okay? At least with the English alphabet. So, for hexadecimal, we can have numbers like BAD. That's a legitimate number. A B is a mapping for the number 11, right? An A is a 10, a B is an 11, a C is a 12, a D is a 13, F is a 15. Base 16 should have the digits between 0 and 15, 0 in the base minus 1. But we need to represent bases greater than 9, or positions greater than 9 as letters in this case. So jumping back down to here, this is BAD. This is 16 to the 0 power. You kidding me? You're embarrassing me. I get it. So, how many times did I do it? There we go. 16 to the 0 power. 16 to the... Yeah, let's do it this way. So 16 16 to the 1. Huh. And this is 16 to the 2. I have a feeling I have an extra 0 on this guy too. Nope. Good. All right, so this is 16 to the 0's power place. This is 16 to the 1's. This is 16 to the 2's. This is the 1's place. The 16's place. I think this is 256. Okay, so to do the conversion, this is 1 times D plus 16 times A plus 256 times B. Well, if we're going to do the mapping, this is 1 times A is 10, B is 11, C is 12, D is 13. So 1 times 13 plus 16 times 10 plus 256 times 11. At the end of the day, that's going to equal 1 times 13 plus 16 times 10, so 160 plus 256 times 11. 2989. All right, so the hexadecimal number BAD is equivalent to the decimal number 2989, 2,989. Make sense? How we did that conversion? And again, exact same pattern, right? Okay. What about going the other direction? $2989 from decimal to hex. Well, 2989 divided by 16 is 186. 186. 186 times 16 is equal to 2976. What does it take to get to an 89? $13. 186 divided by 16 gives us 11.625. So that's an 11. 11 times 16 is 176. What does it take to get to 186? 10. $11 divided by 16 is 0. 0 times 16 is 0. Remainder 11. And then we read our answer from bottom up. So it's 11, 10, 13. But that's not the right answer. We need to convert. 11 is not a single digit. All these different bases, we only deal with single characters, single digits. So an 11 actually maps to a B. A 10 actually maps to an A. A 13 actually maps to a D. Does that make sense? So this is actually a D. This is actually an A. This is actually a B. Now that doesn't mean that all hexadecimal numbers have letters in them. Is the number 25? Is that a legal hexadecimal number? Absolutely is. Well, what number is that in decimal? Well, if I'm going to convert decimal or hexadecimal to decimal, what do? I divide decimal numbers by 16 to get to hexadecimal. In this case, I have a hex number. Hex to decimal. That's this guy. So this is 5 is in the ones place. So that's 5 times 1 plus the 2 is in the 16's place. 2 times 16, which is equal to 37. So the hexadecimal number 25 is equivalent to the decimal number 37. So it's still compressed, right? Just doesn't necessarily, in this case, take up a smaller footprint, but I've represented a larger decimal number in a smaller looking number, I guess. So hex really only helps us from a purpose-driven perspective when we are dealing with smaller space-saving nature. The number actually physically is taking up less space. Now, Abe, you mentioned that hex is for memory, and that I asked you if memory was part of a computer, and you said yes. But then back here, I say that computers like binary. So does that mean computers like hexadecimal too? Is that a guess?
I don't know what you're talking about.
What are you talking about?
Assuming the actual computer does not, but it does. We like it to not use up a lot of space, so we use a lot smaller characters, a lot less characters. That's why we use hexadecimal, so that we can save space.
Tell me about memory. Here we'll throw a Y hex. Abe says memory. That's the correct answer. So you said you've seen memory stuff show up on the screen in hexadecimal. Whatever that means, you've seen hexadecimal and memory seem to be related in some way, right? Okay. What is memory in the computer? What is memory? Or RAM? It's like some of you in here, your computers have 4 gigs of RAM or 8 gigs of RAM, or some of you might have 16 gigs of RAM. A guy in another class has 32 gigs of RAM. So, what is it? What is memory? Why do we need it? What's the purpose of it? Is it just bragging rights? Yeah, I got a new computer, put 32 gigs of RAM in it. I don't even know what that crap's for. I just know it's made by Corsair. It's faster than the other guys. It was 4 times more expensive, and it's got really cool gold-plated heat sinks. Mm-hmm.
Don't forget, you can always download more RAM.
So what is memory? What's memory for? We're making a conversion in this class. We're trying to, this is kind of like we're simulating you like the Borg. When you first came into computer science, we started trying to twist your mind so you stop thinking like a human and more like a computer, right? Because you need to change the way we think, because human beings are we're so good at problem solving. And that's when we started introducing to programming languages. And programming languages try to emulate the way human beings solve problems. And they do that through memory, asking questions, repetition. Okay? Memory, or our memory, how does a computer programming language represent memory? How does it emulate that? There are things called variables, right? What's a variable? Come on, people. It's not even that late. It's like 2:18. We got another 7 minutes in here, 8 minutes in here. Don't check out yet. It's a question that actually should be answered, is what I'm getting at. What is a variable? We can make it a quiz. Somebody other than...
Stored value.
Okay. Name value pair. Name value pair. So a variable is a human readable name associated with a value that gets stored somewhere, as you pointed out. Where does it get stored? So we're sitting at our computer, and we're using Java or whatever. We create a variable, int a, put a 5 there, right? We know from that point forward, when we use that variable a, it will magically become a 5. Okay? But he mentioned that that 5 is stored somewhere. Where? In that expensive gold-plated heatsink thingy. Our computer memory is where values during the runtime of a program are stored. So somewhere, our variable name, A, is holding a memory address, probably in hex, that points to some place in RAM, gold-plated thingy with electricity flowing through it, some bucket in there where the actual value 5 is living, where it's being stored. It's held in stasis. The way RAM works is like electricity is holding through, and there's like, don't forget. Don't forget. And we've done this ourselves, right? Whenever you have a number you don't want to forget, you just keep repeating it to yourself until you get to your destination?
No, I just put it in my phone.
Well, yeah, now we just...
That was before.
Actually, that's kind of true. There's so many things that nobody does today that used to be so commonplace.
And how old do you feel now?
Like, how many of you, like, know more than, like, 2 of your friends' phone numbers?
Family
Wait, my friend.
I'm not saying you're capable of calling them by clicking their picture on your phone. I'm saying you actually know their number.
I know one by heart.
Yeah, I mean, that's...
And she's a stripper.
Apparently I wasted my time stopping the recording before the sodomite joke from her.
What did you learn in computer class today?
Okay, so anyways, we have memory, our RAM. And that RAM is built for storing things in hardware. Teaching our hardware how to remember a value. Okay? And that RAM is divided up into a zillion little buckets. Looks a lot like an array. All right? Now, if you have, let's say that we have 4 gigabytes of RAM. Pretty commonplace now. Most people have 4 gigabytes of RAM or more now, right? All right. And let's just say we're going to use that RAM to store a whole bunch of ints, a whole bunch of integers, 32 bits. So 4 gigabytes, 4 times 1,024 megabytes times 1,024 kilobytes times 1,024 bytes. Times 8. That's the number of bits divided by 32. That's the number of integers we can store in RAM. So that's what? 741,000. 1,073,741,824. That's if we're storing 32-bit values. Now, do we actually always store things in a minimum of 32 bits, or do we actually store things smaller than that? We store things smaller than that. In fact, our programming languages supports things down to a byte. Maybe memory even stores smaller pieces of information. Maybe it stores it in bits. We start getting to very, very, very large numbers. Now that number is bigger than what an integer can hold. So how do we index memory? How do we go to bucket, whatever the very last bucket of memory is? We don't have the numerical capability of holding that value inside of a computer. Computers, we'll talk about processors, they have registers. And registers might be 8 bits or 16 bits or 32 bits. You might even have a 64-bit register on really expensive processors. All right? Well, that might not be a big enough number. So the computer actually represents it in hex and then converts it during runtime into binary. But that conversion needs to be very, very, very fast. Computers are really good at doing math. Okay? But if that conversion is not fast, even the number of steps we're taking here becomes problematic. Then our computer is slowing down because we have to store things in German and at runtime convert it to English, as an analogy. That makes sense? So what we'll look at next time is how we can actually convert between binary and hexadecimal to binary really, really, really quick. But you're going to have a homework assignment. I'll give you this code as a starting point. Again, you can use Excel if you'd like. You can use Game Salad, but I encourage all of you to use Java. I want you to write the methods for converting hexadecimal to decimal and decimal to hexadecimal. Remember, you're going to have to do the mapping for those letters. So, for those of you who are relative beginning programmers, you're going to have probably 6 if statements. If it's a 10, make it an A. If it's an 11, make it a B, so on and so forth. Make sense? Okay, I'll give you this code as a starting point. I'll paste it into Angel so you have it. And I will see everybody on Tuesday. I will be out of town this weekend, but feel free to ask questions, email me, text me, whatever. I'm around. Just I'll be in Illinois.
So considering you've already shown us